Alright, so this video is going to talk about RIP and how RIP builds its routing table. So first off, let's look at our network and see what we have. We have these two LANs on either side connected with multiple links. So this is a serial link and it is slow. This is a fast Ethernet link and it is faster than serial but not as fast as gigabit. So ideally we want our routing protocols to be smart enough that they pick the fastest route across our network. Unfortunately for us, well, not really unfortunately because we have other options, but RIP is not very smart. It picks, its metric is hop count. So it picks the least number of hops. And a hop is a trip across a router. So from this network to that network, the least number of hops is across this serial link. So if we look at our show IP route output for RIP, we're going to 22.2. It tells us to go across a serial link. So that is our least number of hops based on the metric that it is one hop. This number here is the administrative distance. If you hear me talk about that later, that tells you if you have multiple routes from the same to the same place from multiple different methods, it will tell you which one's better. So the lower the administrative distance, the better the method you learn that route is. And we'll look at some of those later on as we switch routing protocols. But at this point, we have a metric of 1 for the serial link. This is, hey, RIP, I want you to go across the serial link. So that's one problem with RIP. It picks slow links by default. So as we go through the lab, you're going to want to get show IP route output. So you're going to want to save it, and you're going to want to label it in such a way that you can put it in your lab report so that I know what I'm looking at. So this would be like RIP show IP route output before failure, because we're about to create a failure. Another way we can look at the route our packets, our traffic is taking is by using the traceroute command, which you should have used in previous classes. If we use the traceroute command, it tells you which hops your router is going through. So in this case, it tells me this packet's going through 11.1, 12.2, and then it makes it to 22.2. So 11.1 is the interface on this router. 12.2 is the serial interface on this router, so it's going to this router, to that router, and then finally making it over to 22.2. So you need to collect that output as well. So same thing. You want to copy and paste, paste it somewhere, and have a good idea of what it is. So you probably want to create a running document right now when you're doing the lab so you can collect those things and keep them in order. So first thing we're going to do is create a failure. All right, we're going to start a continuous ping, and then we're going to shut down or disconnect the serial interface. In the lab, I say you should time how long it takes, so you should do that. I don't really have anything handy to time with because I looked for a timer and I couldn't find one easily. I meant to go get my phone before I started this, but apparently I forgot. So I'm not going to actually time it. That's something for you to do to collect the information from. So I'm going to go to the serial interface and shut it down, and then go back to my ping, and I'm going to look and see how many pings it loses approximately. So RIP, the podcast, so there's back. That didn't take very long. That's probably like, I don't know, 15 seconds. The podcast that went over how the routing protocols work talked about hello times and number of missed updates for RIP. So in theory, RIP sends out an update message every 25 to 35 seconds, and after it misses 6 updates, then it thinks the routing protocol is down. So it should have taken like 3 minutes, but this didn't take 3 minutes because when the interface actually goes down, the router's smart enough to know, hey, that interface is down. I don't need to worry about waiting for updates and stuff like that. So that's why it was much quicker than you may have expected. So basically, we want to go here and look at our routing table again. So do show IP route. And now if we look at that, we see, oh, hey, for 22.2, we're going up to 11.253. And we should know our topology. The 11.253 is this router. So we go up here and look at our routing protocol, our routing table, and see where we're going for that traffic. 22.0, oh, we have 2 possible routes for that. We have one across fast Ethernet and one across gigabit Ethernet. And that's kind of cool. And why is that? Well, a lot of routing protocols, if you get equal cost metrics, it'll use both routes. So in this case, they both have a metric of 2, meaning they're 2 hops away. So it put both routes in the routing table, which is good. And that's kind of cool. So we'll do traceroute on our PC to collect that for submission. So this confirms what we saw by looking at the routing table. You know, 11.1, 11.253, 22, 21.2. If we run it again, we might get different results. Oh, check that out. This packet went a different way. So that's kind of cool. We're getting different results because we have multiple routes. So again, at this point, you want to go collect your show IP route output, copy and paste this in your trace route. Now we're going to create another type of failure. We're going to create a failure this time that the router's not going to know about for a while. And what do I mean by it's not going to know about for a while? We're going to break this link between these two switches, and then this router's still going to think that link's up. So it's still going to think it can send traffic even though it can't because the link between the two switches is broken. So we're going to start our ping again. And this might take a while for it to recover. So we're going to start our continuous ping. We're going to go break this link, and then we're going to look at a few things in the router. So first off, I broke that link, but if I do show IP int brief, the router still thinks the link is up. If I do show IP route, the link is the route's still showing up. Both of the routes are still there, so that's weird. So what does that mean for our traffic? Well, it probably means we're getting about half of our pings back. Sometimes it's working, sometimes it's not. So it broke a little bit, and it worked a little bit, and it worked. And it broke. So basically, we have these two routes, but it's working unreliably at this point because one of the routes is still there when it shouldn't be. And the reason that is like I just said, RIP needs to miss like 6 updates before it will decide that the route is down. And we can tell how long it's going to be by looking at the show IP route output. This time over here is the time since the last update. So the one that's working got an update at 9 seconds. The one that's not working got an update at 1 minute and 2. So at some point, this is going to clarify, this is going to clear up, and the ping will start working again. Another thing you may not have thought about is when we send traffic, we ping over, but then the reply has to come back also. So by breaking this link, I've also broken the routing on this router. If we look at this router, it's also not getting updates from that other router that it's connected to. So it's trying to get back to 11.0, and it has 2 routes for the 11.0 network, one across a gig network that's still up, but it has this other one where it hasn't got an update in 1 minute 41. So at some point, probably around 3 minutes, I probably should have tested this before I made the podcast so I know exactly. At some point, we're going to get to the point where this route gets marked as possibly down, and hopefully it stops getting used and our ping gets back to more reliable. So we're going to hang out and wait for this to happen. So we're at 222. 226. Ping is still unreliable. $241. I didn't start a timer, but this is just as good as a timer almost. 250. 255. 258. Oh, hey, 3 minutes. Hey, it thinks it's down. Now we're going the right way. Let's go check and see if our ping's back up more reliably yet. Still not really reliable, so let's check this other router to see if the return traffic is broken yet. Oh, hey, now it says it's down, routing it via 21.1. So it seems to still be using the bad route. Now it looks like, okay, so it looks like we're back. So it looked like it decided it was broken, and then it took a little bit longer for it to start working. So now if we go look, hopefully we only have one route. So now we only have the good route. So that, I mean, if you think about RIP when it was invented, it was probably in the 70s, and back then having your routers take 5 minutes to recover wasn't really a big deal because that was 5 minutes was far faster than it was taking you for you to drive in and fix the static routes. So, you know, it wasn't bad for the time. But nowadays, when people are making tons of money on the internet and we have better options, RIP's just not a good option for a routing protocol for pretty much any reason. So I'm going to go ahead, I'm going to connect these two links back together, and we're going to see what happens. see if it comes in seamlessly or if it breaks again. Sometimes when your routing protocols fix things, they break. It's like, oh, hey, it should work, but it's not working. So I thought I did. Oh, those are. I'm like, I thought I did turn on port fast, but these are two switches connected, so it needs to do the port fast. So we're going to have to wait 45 seconds before it's actually up and communicating. So we still have the one good route, which is to be expected. Wait for these guys to go green. All right, they're green. They send updates every 25 to 35 seconds. So, oh, hey, we have the route. We have the route back in. Let's see if we lost any pings while that was happening. No, we didn't lose any pings while that was happening. So that was good. If we do a trace route now, you don't need to do this. You don't need to do this trace route to collect for submission when you fix it. But we just want to look. Oh, hey, it's going across the expected route. It's using both of those expected routes, so that's good. We're going to go ahead and put the serial link back. Turn that guy back on. And now we should get, this guy should get back to being the route it takes across the serial link. So yeah, so now we're going across the serial link again. So there we go. So we're going across the best path as selected by RIP, which is the slow path using the serial link, which means RIP's probably not a very good routing protocol to use in most cases. So a couple other things we want to look at with RIP. We looked at the routing table and stuff, and another thing we want to look at is look at my lab sheet. We want to look at the debug output, right? So sometimes if you're not seeing what you expect you want to see, you can look at exactly what the routers are saying to each other. And we can do that for RIP with the command debug IP RIP. And it will show you the update messages that your router is sending and the update messages that it is receiving. So we send them about every 30 seconds, so we'll just wait to see what comes in. So here it says I received an update from 11.253, which is the table 1 top router. All right, we're going to wait till we get one more update, and then we're going to stop the debug. All right, so we're going to do undebug all. All right, thing about debug is it's useful if you know what you're looking for, but if you don't know what you're looking for, it's just a lot of nonsense. So we're going to try to understand what this is doing. So you can do undebug all to turn it off, or you can also do no debug IP RIP to turn it off. And you might want to keep in mind that if you turn on debugging, it uses CPU. So if you have a very busy router and you turn on debugging, it's probably a bad idea. So here we received an update from table 1 top, and it basically told us about the networks it knows about. Here are the networks I know about and how long it takes me to get to them. So my router would use that information to decide if that's a better route than it already knows. And if the network's stable, nothing's changing. These are just going to be the same thing over and over again. Here's what it looks like when it sends an update. It needs to send an update to 224.0.0.9, which is the multicast address for RIPv2 routers. It sends one out faster than at 00, and it also sends it out on the LAN. And you may or may not want that to happen. If you don't want that to happen, you can make that a passive interface, but we're not going to talk anymore about that. And then in the update, it sends out the routes it knows about with the hops to get there. So basically it says, hey, I know about these 3 routes because these 3 networks because I'm directly connected up to them. And I know about these 3 networks because I learned about them from that other router I'm connected to across a serial link. Of course, it doesn't say in there anything about a serial link. It just tells it what it knows and the metric to get there. So that's debugging output. You want to look at that. And let's make sure there's nothing else I need to talk about with RIP. All right, that is really all I want to talk about for RIP. If we're in the lab, we're going to do some throughput testing to further confirm our slowness across the slow link. But if you're using the simulator, we're not going to be able to do that. So next step is going to be disable RIP and enable OSPF. And I'm going to do that in the next podcast.